All right. Hi, everyone. For those of you who don't know me, I'm Jay. I was the other Unidata intern this summer, and I'm going to talk to you a little bit about what I'm doing. So we talked about Lin Feng and what he amazingly did with the C++ and the NetPy, but I'm going to talk about performative benchmarking of NetPy with ASV in a CI/CD workflow. And we will get to what all that word soup means in just a minute. There we go. So let's talk a little bit about the motivation, why we originally wanted to benchmark NetPy. So this all came back to what Lin Feng was doing. C++ification, as we have affectionately termed it. Lin Feng is helping those slow functions that he's talked about run much faster. The thing is, we need a way to quantify this, right? We expect it to run much faster, but we want to make sure that's what's actually happening. And that is where performative benchmarking comes in, or timing the code, seeing how fast it's running, making a change, and then seeing how fast it's running again. Benchmarking also has other benefits, so it's great to incorporate into that NetPy. Benchmarking also identifies bottleneck functions, so we can look and say, oh, this is running much slower than everything else. What can we do to change this? It also shows us when user changes change the performance of the code, for better or for worse. So we're going to skip ahead a little bit to the end of what I got to. So this website is where you can see the ASV results. If you try to go to it right now, it will not work. It's live, but there are no results on it. The results will be on it before I leave, but for today, let's go ahead and cheat a little bit and just use my development version of the website. We'll do a quick demo. All right, so this is my development version. Again, functionally will work the same as the one that goes into production. So we're looking at the top here, we have a bunch of like this. These are the apparent temperature benchmarks. These are the boundary layer turbulence benchmarks. These are the dry thermodynamics benchmarks. And we keep going down. We can see we've got a lot of benchmarks. I think I have every function in the calc module of NetPy benchmarked, but I could be wrong. So each one of these little tiles is a different function. So for example, like this is the density function, and then the line is how fast it's running. So let's take a closer look at one, if I can find, this is the wrong section. If I can find it, here we go. So we're going to look at LCL as an example. So up here on the x-axis, you can see that this is basically the history of NetPy. We start at version 1.4.0. Anything before that, the dependencies get really weird because Python versions get weird. So we just decided 1.4.0 is far enough back for us. Keeps going through all the minor versions, and then this is present day. We can see on the x-axis over here, this is milliseconds. So something that might be a little confusing is we want a low line. Low line means faster function. It's a little backwards from what you might expect, but you do get used to it. ASV is really cool. It has a bunch of these options over here. It shows you this is the starting commit hash that we used. This is the ending commit hash, or the most recent one that we benchmarked. Ton of fun little plot settings if you want to play around with those. It also shows us the machine and its specs, and we'll talk about why it's called Docker container a little bit later. But for now, let's take a closer look at this line. So we see recently it dropped pretty substantially, right? And that's good, but let's think about why did that happen? And one thing that's fun is if you click on a dot, it will pull up the GitHub commit hash of what that dot was. So this is actually something that Drew made this spring, and this is where we went from a iterative to an analytic LCL calculation. And the whole point of this was to make LCL run faster. So the drop of that in our graph is like, yes, that's good. That is exactly what we wanted. And now we know how exactly by how much it dropped. So as well as the benchmark grid that you can take a look at, we can also take a look at the benchmark list, which is what Lin Feng showed us earlier. So we've got the names of all the benchmarks, the most recent commit hash that we've run, how fast they ran there, and then recent change in percentage, and then a little information about how and why it changed. So I'm pretty sure that the current threshold for it saying, hey, there was a recent change is about 10% difference. So
the change is from pure Python to blended. Yeah.
This is all in the NetPy repository. There is no C++ in the NetPy repository yet. So the red changes are going to be anything that's 10% or more slower. The green changes are going to be anything that's 10% or more faster. So let's take a look at saturation vapor pressure, right? This dropped 40% basically. That's kind of strange. And it did it fairly recently. So if we click on this, we can actually see the diff and these two commits that change between. And if we look at this, this is another Drew contribution. And this was going to a more accurate saturation vapor pressure function. However, we did know in advance this was going to slow it down. So, right, so this makes sense. It tracks. Yeah, a slower function might not be better, but it's more accurate. So we're cool with that. And we can also, oops, I always do this. Thank you. Come on. Okay. Go back to the benchmarks list and let's say, oh, well, here's LCL again. Why don't we take a look at this diff? And I'm going to open in a different tab this time. And again, we see these same commits that Drew committed that we expect to change it. So we can take a look and see what's happening and be like, okay, that tracks that change. Or we can look at it and be like, that shouldn't have changed based on what changed. We need to dig into that. So it can be a very useful tool. Like I said, you have this presentation. Eventually, those will be live. I definitely recommend going and playing around with it. ASV has a lot of fun settings that you can mess with. So let's dive in a little bit into the nitty-gritty of what we actually did to make this work. Don't worry if you're not like a software engineer. I'm going to try to explain it as best I can to a general audience, just because I want everyone to kind of understand it here. So if you work at Unidata, you probably know GitHub. This is where we store the code for all our repositories. Within the MetPy repository, I have a pull request open for a benchmarking folder. This contains everything that we need to run the benchmarks. That's functions, configuration files, a couple of shell scripts for the continuous integration, continuous deployment environment, all of that fun stuff. We also created a new repository that is the MetPy benchmark repository. And we didn't want the results of the benchmark runs to clutter the MetPy repo too much. So they're now in this new MetPy benchmark repo. Airspeed velocity, you'll probably hear me never say its full name again. It's ASV. It is an open source Python benchmarking package. It's used by things like SciPy, AstroPy, and NumPy. So it's pretty tried and tested. So basically what ASV does is you give it a commit hash from the GitHub, takes a look at it and says, okay, this is how the GitHub was during this commit hash. So I'm going to make a copy of this in its own environment, and I'm going to run the benchmark on it and record how fast it takes. If you give it, like we do, a bunch of commits, it does that for each one and then strings them together and says, this is what happened over the history. And then one of the best parts of ASV is that pretty HTML format we looked at. That's all automatic. It's just one command and it'll return everything very easily, digestibly. There we go. Jenkins. So Jenkins is we have a Jenkins instance here at Unidata. It is used for those continuous integration and continuous development workflows. The reason we use this instead, some of you with a little more CI/CD knowledge might be like, why didn't we just use GitHub Actions? It's integrated into GitHub. The issue is GitHub Actions has a tendency to run on a different runner each time. And because we want to take commits and results and concatenate them together, we want consistent hardware, and that's where Jenkins comes in. It runs on a machine. It's called ML11. You would think it's in Mesa Lab, but we have no idea. But it's always run on the same machine every time. And that means that we are getting consistent results, and we're able to concatenate them over different runs. This was a big hurdle that we came through, and this was something that Jenkins really helped us out with. Docker software, my favorite. So for those of you who don't know, Docker software, which I'm not allowed to call just Docker because it must always be used as an adjective, is a containerization application. So what it basically does is it runs code in a semi-isolated container from the main machine. We did not want to run the benchmarks on the bare metal of ML11 just because it's creating a lot of file paths. And if we accidentally created something by root, everyone who knows root in Linux, creating those file paths, we could accidentally make something that cannot be deleted. And we did not want to do that. So this Docker container enables us to run it, and we run it as the user called Docker container, like we saw earlier. That way we don't accidentally accidentally mess up what I'm sure is a very expensive machine. Docker is also portable. So in theory, anyone with a Docker engine should be able to run the little Docker command that we have in the docs and run it. Run all the benchmarks, but it has been tested. We did it on Windows and Mac. So, and ML11 is Linux. So we've done all three of those machines. Finally, even though we are using Jenkins, GitHub Actions also has a place in our workflow. So the MapPy benchmark repo has that GitHub action, and it uses ASV to generate that pretty HTML using an ASV publish command. This enables it to make that artifact and then push to that pretty site that we saw earlier. So how does benchmarking with ASV work specifically? So this is the file tree that is going to be added to the GitHub MapPy repository. So you'll see a bunch of .sh files. Those are shell script helpers. They are basically helping Jenkins and Docker run these commands without having to individually run each command, right? They're helping our workflow be a little more clear. The Jenkins file tells the Jenkins instance how to run, whereas the Docker file creates a Docker image, which then creates the Docker container. You'll notice we do have an ASV results directory, and you might be like, wait a minute, you just said you're not putting results in this repository. Well, we aren't, but ASV wants to have a place that it can put results because it wants to see that benchmarks.json file. That's how it finds the benchmarks, and it stores it in that results directory. So that should be the only file that's ever in there, but we do technically have a results directory. That asv.conf.json is the configuration file for ASV, so it helps everything run on MapPy smoothly. The benchmarks directory within the benchmarks directory contains the benchmarks. So as you can see, all those .py files, and we'll look a little deeper into what's actually in those, but these are the actual functions that we're timing to see how fast is stuff running. Finally, you'll notice right below that there is this data array generate.py file. And this is because for the benchmarks, I wanted a consistent data set of data. So I created this 4D artificial data set with all of the variables that we could need for these benchmarks and created it and put it in that data array generate.py file. Now, it is 50 lats, 50 longs, 50 pressure levels, and 3 times over 16 variables. It is a huge file, so there is no way we're going to store that in the MapPy repository, which is where that data array generate.py file comes in. We tell Jenkins or local users who want to run benchmarks, just execute that .py file, and you'll get basically this data set. And then it can use it to its heart's content. But you might be thinking, okay, that's great, but ASV needs a way to access this data set within the benchmarks. And that is where we have some ASV methods come in. Within each of those .py benchmarking files, we have one setup cache method. And this method basically takes the data array generate.py, it takes the generated data array and parses the netcdf format to come up with that data set. This runs once before each benchmarking file, and the results are cached. By contrast, there's also a setup method where we take this DS data set and slice it like we need. So, for example, a time slice is kind of what I showed you on that slide earlier. It's the data at one time. Pressure slice is at one pressure level. I do profile slices where the lat and ln are held constant, but we just go up in pressure and see how the variables change. So as you can see, we've got a lot of that sort of stuff, and that is the setup method. The setup method runs before each individual benchmark, and this is because it doesn't take very long, whereas opening the data set takes longer. So we just do this before each benchmark, kind of refresh everything, get it all good to go for the next benchmark. This is an example benchmark function. As you can tell, I have an affinity for the LCL function. So we pass this time slice, and basically what ASV is going to do is it's going to measure anything that's within this function. So we have the time, which is how ASV knows that it's a benchmark, and LCL. So in the function, I'm using npcalc.lcl, and I am using the pressure, temperature, and dew point values from that slice. ASV is then going to see this, run it a couple of times, then average the results and say, okay, this is reliably about how fast this is beating. So that is how benchmarking works. Let's talk a little bit about how the actual workflow runs. I'm going to give everyone a fair heads up. My flowchart is not quite as convoluted as Linfeng's, but it is still fairly convoluted. I'm going to take it slow. Please stop me and ask questions if you get lost. So the first part of this, that's a little smaller than I thought it would be. Oh well. The first part of this is Jenkins is triggered every Saturday morning automatically. It's between 3 and 4 a.m. We're all asleep. It's doing its thing. Next, Jenkins is going to make a clone of NetPy so that it has a copy of the NetPy repository and it can do whatever it wants to in its workspace without changing the source code. Next, Jenkins is going to use one of those shell scripts and it's going to look at the history of NetPy. We currently, like we saw earlier, have it set up, okay, the first commit tagged with every minor version of NetPy, we want that one. And we also want every human-made contribution of the most recent version of NetPy. Those commit hashes are gotten, and then they're saved into this file, which you probably can't read, but says no-bot merge commits.txt. So that is saved. These are the benchmarks that we're going to run on the hashes that we're going to run. So we save those, make sure we have them. Next, we want Jenkins to be able to see the existing results that we already have. So from the NetPy benchmark repository, we copy over the existing results into the workspace so that Jenkins can see them. It knows what we've already run. Next, Jenkins uses the Docker file to create a Docker image, which then creates the Docker container, and then it enters the Docker container. Yeah. It also gives the Docker container a mount of that workspace, so it's able to change the workspace as it pleases, and it can do whatever it wants to it, so it can add results that we're going to see. So up next, we use a Docker run command, and the container runs the benchmarks on the commits that we've given it. So it sees all of those commit hashes, and ASV says, I'm going to run on all of these, unless we already have successful results for commit. And then it's going to say, why would we run them again? That's just a waste of time. So the only way that ASV is going to rerun benchmarks for a commit that already exists is going to be if the benchmark version has changed. Because in that case, the benchmark functions might have changed. And that means that if we're concatenating results, it might not actually be consistent. So we instead, if that benchmark version has changed, it says, okay, I know to overwrite the old file. And if there's any new commits, basically this will be like human-made contributor commits in the past week. It's going to go ahead and run the benchmarks for all of those. Next, we don't want a persistent Docker container on ML11, so the Docker container self-terminates and passes responsibility back to Jenkins after it saves those results back to that Jenkins workspace. So now Jenkins is going to go ahead and push the results, old and new, right back to that NetPy benchmark repository. Now, some of you may cringe when I say this, but I know forced pushing is usually really bad practice, but it's what we do here, right? We're not overwriting any files because we copy everything to begin with and then just add to it. Nobody else should be pushing to this NetPy benchmark repository, so it's not like we're going to overwrite anyone's work. And at the end of the day, we don't really care about the commit history of the results, right? We only need the results as they are now. So just to make sure that the push actually happens, force pushing was our best option here. So now that we have pushed to NetPy benchmark, the GitHub action is going to say, okay, you've pushed. That's great. Let's create the HTML for the static page so that everyone can see the up-to-date results. So it does that, and then the GitHub action also deploys it to that site that we saw earlier. And then the workflow is finished running. It, in theory, takes about like half an hour total, but it depends on how many commits it has to run, right? But again, it's 3 o'clock in the morning. I don't think anyone is going to be doing anything else on this machine. So you may be thinking, okay, all of this is great, but what happens if we merge a commit and the workflow runs and we realize that it absolutely destroyed our time efficiency? We don't want that to happen, so we are going to use something called comparative benchmarking. ASV is able to do this on command, and it is you're going to say, okay, here's two different branches or two different commit hashes. I want to compare what's happening between them. ASV has that built-in function, and when you combine it with GitHub Actions, it can automatically do it on pull request. So we have I don't think I've opened the PR, but it'll be merged by the time I leave. We have a main branch. We have a GitHub action that's going to say, okay, we are going to compare our current main branch with what you're trying to push. We only do this if a PR is labeled because ASV is kind of slow and it takes 10 minutes. And if PR is obviously not going to change anything, then we're just not going to run it. So currently a benchmark failure occurs when any benchmark is 10% or more slower. This can be changed if we're like, okay, GitHub Actions is just not good at this. We need a little bit more. Or if we're like, actually, let's make it 5%. We can do that in the future. So this is an example, also really small, but this is an example from when I was developing the GitHub action. I had a fake branch that I put a sleep function and a scale height function for 2 seconds, which on a function that was before taking 3.1 milliseconds, that was a 600% difference. So maybe a little bit of a dramatic difference, probably not something that we actually see, but we can see that ASV looked at this and said, that's much slower, and that is a problem. So it went ahead and failed this benchmark run. We can see up here this 9.5-minute run. Again, that's why we're only doing it on PRs that we're going to label with benchmark. Even before you open a PR, you might want to look at your results and see what's going on there. So we can run local comparisons if you have ASV installed and you have untouched local main branch. So this is, thank you, Linfeng, for the test C++ K branch. So this is where we're comparing some benchmarks with C++. So we can see this is the output that you get from the comparative benchmark. This is a little bit edited because it can be a little bit verbose, but this is a little easier to understand. So we can see we're comparing the main branch, which is just MetPy, with the test C++ K branch. So we can see that the dew point function is 98% slower, right? It went from 2.46 milliseconds to 4.85 milliseconds. That's something to dig into, right? Like, we're not sure why that's happening. Let's take a look at it. So that gives us a heads up of, let's see what's going on there. One function that is so much faster is the wet bulb temperature function. That went from 8 seconds to 280 milliseconds, a 97% decrease, which is absolutely nuts. Props to Linfeng. So we can see that and be like, okay, that tracks. I was literally putting in code to make that faster, and now it's faster. That's great. One function that hasn't changed significantly is the pressure to height standard function. It changed about 2%, but we went from 852 microseconds to 866 microseconds, which running on my machine that probably has like 5 programs open and running it, it's probably just noise, right? Like that 2% doesn't really matter. So that's where that 10% tolerance comes into play. And that also makes sense because Linfeng hasn't touched anything that touches pressure height standard. If that had changed, it'd be weird. And that would also be something to dig into. All right, I think that is my presentation. I am happy to take any questions. And like Linfeng said, I would not be here without the help of all of you in this room. So thank you all so much for everything that you do.
Jay, and if there are questions online, raise your hand and I will call on you. For anybody here in the room?
As you were doing this benchmarking, did any surprises emerge, things that you didn't expect?
I found something new every day. I actually made, I don't have it with me, but I made a call chart of MetPy and like what each function calls, because I'm looking at a lot of these things and I'm like, this is much more intertwined than you would expect it to be. So you change one function and it changes 15 others. That's a little bit of an exaggeration, but there are some that connect to like 8 or 10 other functions. So it's kind of learning about that and realizing how interconnected the entire code base is. I think that was one of the big surprises for me. And like looking at this benchmarking and being like, okay, it was actually really hard for me to find a function to put a sleep function in that would only change one function. Scale height ended up being the one, but just trying to find stuff like that, seeing how it's all interconnected, and really seeing how those changes that Linafeng made, he didn't even touch wet bulb temperature. He just touched its dependencies, and then it's much faster.
You can see the diagram that Jay made, the spider web of MetPy's code base in the Slack, or if you happen to stop by his office, it takes what, like 6 sheets of paper to
That I
spread
would-
across.
Yes, and have written on, and someone can inherit when I leave.
But take a look.
Other questions?
Good statement. I know 11's in the case of that.
Good to know.
Number 6 is solution.
And nobody's working there at 3 a.m.
Just mission.
It's doing a lot of work for us. Why, I guess to that end, why does it matter for us to, you explained why we should pick our own machine, but why are we running it Saturday in the middle of the night?
So the Unidata Jenkins machine does sometimes run other things. It has threads tests that it can do. It has some NetCDF Java tests. And while in theory it's a Docker container, right, it shouldn't matter. We accidentally ran 2 things at the same time and it didn't, right? The graph was crazy and I was looking at it and panicking and being like, what just happened? And then I asked Sean, he was like, oh yeah, a test was running. So right now, nothing else runs at Saturday at 3 in the morning, and nobody should start a manual run at Saturday at 3 o'clock in the morning. If you do, we have other issues that we need to address.
For sure, thanks.
What language is ASV written?
So ASV is primarily written in Python. I think it might have 1 or 2 things where it actually does call some C++, like Linafeng's, but it is mostly Python.
Yeah, I think Jay was describing the code that takes your snapshot, builds an environment. I think that step, it uses some C++ code to speed up making, deconstructing environments.
When you like Conda install ASV, it installs Pybind 11 as a dependency. So it uses that as well. I'm like 90% sure.
So if you had airspeed velocity is primarily a Python tool because the name airspeed velocity is playing off of the reference in Monty Python, the Holy Grail.
And it has a workflow engine inside it to sequence
At least in terms of calling the benchmarks, yeah.
calling them.
It's command line arguments that you can put in to be like, I want to do all of these commits.
And then I know we're over, but I'll ask you the same question I asked about Fung. I guess Julian already asked about surprises, but what is something you are glad to have learned from this summer? And then is there anything that you ran into that was particularly frustrating or stubborn or?
One thing I learned that was a little frustrating is the importance of good documentation because I worked with some packages that I won't name that did not have it. So I spent a lot of time spelunking in source code, and as a result, I have a 30-page document on how ASV works now because I do not want anyone to have to do what I did. So that is something that I learned and a skill I'm glad I have. I think what I'm most happy to take back to NC State with me is just a lot of the programming problem solving that I have now. Like if you had asked me to debug ASV, this Conda install 6 months ago, I would have been like, but now I can be like, okay, I know how to use the terminal. I know how to look at standard output. You know, I know how to troubleshoot things that are going on with this. And that's something that I'm really glad I learned in this project. And now I can take it all into whatever I want to do in the future.
Just to follow on your last comment, and this is to both of you, will you be taking back the work you have done and continue to work on it or integrate it into your work going forward?
If I ever make a Python code that needs to be benchmarked, I've got that down. But I also don't intend to stop messing with MetPie here. It's a community driven thing as well. So maybe I'll pop in on the community call sometimes or doing things like that.
C++, um, there are still a lot of things need to be improved. We're still working on that, and I hope to witness, my code can be merged into the main code and can be used by all the community members. Yeah, towards that goal, there are still a lot of works to do for me. Yeah.
Before we wrap up and give everyone a clap one more time, I do want to share, I know we're already a few minutes late. I don't imagine many people in the room are quick to forget what May of 2025 looked like around Unidata. Jay and Lin Feng started when there was no one here in the office but me and Ryan. We only had one project that could pay for their time. We said, hey, Ryan reached out to them before they started, like, this is going down. Do you still want to come participate? They both said, yes, absolutely. They both said, yes, I'll work on the project you have for me. We laid out some options and we're like, in previous summers, we don't always pick one big project, or we sometimes let people just practice multiple small things all summer. What would you like to do? And they both adopted these intense, longer term, like, committed projects that were dependent on each other, dependent on me and Ryan, and basically adopted them as their own children for the entire summer and produced real, like, things we told the NSF we would deliver on our grant in the scope of the summer, starting in such intense and weary and scary circumstances. And so intense props to y'all for coming and making it work, hanging out alone in this building with me and Ryan for a few weeks. Lucky and thankful that many people were able to return shortly after, but props and thanks to y'all for making it work and really showing and doing a lot for us with us this summer. So thank you.